Welcome back to another video. So we're starting sequential logic design with this video. And sequential circuits are generally more complex to design when compared to combinational circuits. So if you remember when we started the logic design, we had actually used a really simple rudimentary definition of a sequential circuit. We defined this as a circuit whose outputs, so sequential circuit, we had defined it as a circuit whose output at any instant of time depends on current inputs and previous outputs, right? And this was the schematic. This was the general structure of a sequential circuit. So it will always have some current inputs. So these are my current inputs. Then I need to store my previous outputs. So memory is basically where we store our previous outputs. Remember, the memory appears in the feedback path. And then together, these current inputs and these previous outputs, they will give us our current outputs, right? Now I'm slightly going to change the definition here in the sense that these previous outputs define what's known as the state of the circuit, right? Because these previous outputs are stored in this memory unit. So every time we have a sequential circuit wherein there is a memory in the feedback path, whatever binary information is stored in this memory, it constitutes the state of the sequential circuit. Right? So this is a new term that I'm introducing here. You will later on see the significance of this term, because based on this term, we'll be actually coming up with a general methodology to design sequential circuits. Fine. So based on this, we can say that the output of a sequential circuit depends upon the current inputs and the state of the circuit, right? Now, if you see at the schematic, the new thing here is this portion, the memory part, which now, as per our definition, stores the state of the circuit. So first thing, before we actually go designing sequential circuits, we will have to actually discuss how do we design memories, right? And we'll start with the basic. You know that the basic unit of memory is a bit. So basic unit of memory in digital is a bit. This is the smallest unit that can have. And bit can have two values, 0 or 1. So we'll start with the basics. We'll start with a circuit. We'll come up with a circuit that allows us to store 1 bit. Because when we know how to store a single bit, then we can replicate that unit and we can then store multiple bits, right? So when I say storing 1 bit, what I actually mean is that storing 1 bit in the context here means that we need a mechanism that allows us to, so we can put it something like this: we can save a bit in some circuit, in some block, fine, and later we should be able to retrieve it. This is the concept of memory. You store for some time, but then there should be a mechanism to read. That's what we call write. Writing means storing that bit in the memory, and then there should also be a mechanism. We should be able to retrieve that bit. This is important. Should be able to retrieve the bit. And when I say bit, I need a circuit that allows me to store both 0 as well as 1. Fine. Now consider this circuit. Here I have an OR gate. This is a simple OR gate. And one of the inputs, I'm calling it S, and the output I'm calling Q. Fine. Now, if I make a small connection here, if I make a connection something like this, I tape this output and feed it back as the second input of the OR gate. Fine. Then what happens? Let's assume that initially S is equivalent to 0. Fine. Now, since S is equivalent to 0, then you can't actually tell what Q is. Fine. But after some time, let's assume that at some instant, S changes from, yeah, S now becomes 1. Now, you know for an OR gate, if one of the inputs is 1, output will always be 1. So at some instant, S is equivalent to 1, which means at this instant, Q will also change to 1. Fine. Now, what is important, once Q changes to 1, so S is equivalent to 1, means Q is equal to 1, then I am feeding this 1 back to this. So this means even if later on S changes back to 0, since this input is 1, this circuit, this small OR gate, will continuously store 1. So this is what is reflected in this small timing diagram here. Initially S is 0, so Q is, you can say it is 0. But S changes to 1 here, there is some delay associated with this, and then it changes to 1. Then even if S changes back to 0, Q will continue to stay at 1. Fine. Similarly, the complementary circuit we can construct using an AND gate, wherein I have this input R and the output is Q. So in this circuit, if initially I assume R is equivalent to 1, Q can be anything. Then again, if I have a feedback connection from output to the input side, and when R changes to 0 at some instant, you know for an AND gate, if one of the inputs is 0, output is always going to be 0. So as soon as R changes to 0, Q will change to 0. Because of the feedback connection, this output, this input will stay at 0. That even if R changes to 1, Q will stay at 0. Again, this is reflected here. This is 1. It changes to 0. So Q goes to 0. Even if it changes to 1, this will continue to stay at 0 indefinitely. Fine. So using these circuits, we are able to store, so using OR gate, we are able to store binary 1, and using an AND gate, we are able to store 0. But using an OR gate, we cannot store 0, and using an AND gate, we cannot store 1. Whereas our requirement is we should come up with a block, we should come up with a circuit that allows us to store both 0 and 1, and later on there should be also a mechanism that allows us to retrieve 0 and 1 if and when we require it. Right? So this kind of circuit, it cannot fit our purpose because of this problem. But an important point here is that in both these circuits, in both these OR gates and AND gate, the important thing here is that these are based on feedback. So what it tells us, to come up with a circuit, to come up with a block that allows us to store bits, we should have some sort of feedback connection. So this is the reason I started with this example. Obviously, these are not practical circuits because of the problem that this can only store 1, this can only store 0. And we need a circuit that stores both, and later on we should be able to retrieve both 0 and 1. But an important point here is it gives us an idea that to store and to come up with circuits that store bits, we need some sort of a feedback where the output is being fed back to the input, and that feedback actually allows us to store data. So with this basic concept, in the next video we'll be actually coming up with a practical circuit that allows us to store both zeros and ones, and later on allows us to retrieve 0 and 1 if and when we need it. Fine. So that will be taken in the next video.